So, hi everybody. My name's Ashley, and I'm a lecturer in planetary science at the Open University. When I'm not in lockdown here in my house with the cats, I usually found in a laboratory studying meteorites using electron ion beams and X-rays to try and work out what their mineralogy is. And so I thought I'd take this opportunity to introduce the idea of meteorites. What are meteorites? Why do I care about them, and why are we interested in studying these rocks that come to us from space? And so I'm just going to share my screen. So this is Meteorites 101. I'm hoping that I'll be able to find time to make a couple of these introduction lectures. So hopefully I'll do one on meteors and fireballs and what happens when bits of rock from space come traveling in through the Earth's atmosphere, and how we can use cameras to actually find those bits of rock. And also, hopefully, I'll do one about asteroids, so the source of most of the meteorites that we have in our collections. So one of the big questions we have in science is how did our solar system form? And so we know our solar system is about 4.5 billion years old. And so obviously there wasn't anybody around at that time to actually see the solar system forming. One way we can actually tackle this question is to use telescopes and to actually look at other planetary systems that are forming out there in space. And so what you can see on this slide is a picture of the HL Tau system that was taken by the ALMA telescope that's out in Chile. What you can see in this image is there's a kind of central bright region, and this is the central star within HL Tau. And this is a really young star. This is probably less than 100,000 years old. This whole system is about 450 light years away from the Earth. So if you remember, a light year is the time it takes for light to travel within a year. And so around this central star, we see these kind of bright and dark rings of material. So this is gas and dust in this disk around the central star. And we call this the protoplanetary disk. And so this is where materials are accreting together, all that gas and all of that dust coming together to actually start making planets. And so we're actually using telescopes to witness the birth of planetary systems. And we can use these images to actually try and understand what was going on in our own solar system 4.5 billion years ago. And what we think is going on in this picture is you kind of have these bright regions, and this is the gas and the dust, and then you have these kind of darker rings around here. And that's probably where this gas and dust is being swept up and accreted into planetary-sized objects. So really amazing images that we can collect these days using telescopes. And if we compare this system to our own solar system, just to give you an idea, this is roughly where the orbit of Neptune is. So this is about 30 astronomical units away from the central star. So one astronomical unit is the distance between the Earth and the Sun. It's about 150 million kilometers, or about 90 million miles. So Neptune is 30 times that distance away from our own Sun. And so this is where it would be roughly in the HL Tau system. And this is where Pluto would be. So Pluto is about 40 astronomical units away from our Sun. And what you can see, though, is there's this kind of central region in the HL Tau system, which is very, very bright, very close to the star in the middle. And we actually don't see any kind of rings within there. We don't see very much structure. We can't really infer what processes are going on with that part of HL Tau using the information that we have from telescopes right now. What we know, though, from our own solar system, that there could possibly be a whole range of diverse materials within that region. So we know within our own solar system that we have inner rocky objects and planets like the Earth, and obviously Mercury, Venus and Mars. And as you go slightly further out and the temperatures drop as you get further away from the Sun, you start making gas giant planets, ice giant planets like Jupiter, Saturn and Uranus. And so the telescopes are really amazing for enabling us to see the birth of these planets, but we're still kind of limited in the amount of information that we can get back from telescopes. So our solar system is kind of special because we're able to actually send out spacecraft to observe all the different planets, moons and other objects that we find within our solar system. So we can go and explore places like Mars and the Moon and Jupiter and Saturn using spacecraft and using techniques, remote sensing techniques, to try and learn about those planets and piece together the kind of history of our own solar system. This is something we're not able to do for other planetary systems quite yet. Our solar system is also really special because it's the only place where we can actually get physical samples of other places within our solar system, bring them back to Earth and study them in the laboratory. So rather than kind of using a telescope to look at an object that's 450 light years away from us, we can actually collect a piece of rock, say, from the Moon, bring that back to the Earth and analyze it almost atom by atom in our laboratories. And so this changes the kind of magnitude of information that we can learn about how our solar system formed. So I mentioned the Moon, and so we can actually go and collect samples of other planetary objects within our solar system. And so one of the places that we've successfully been able to do that is the Moon. In the late 1960s and the early 1970s, there were 6 Apollo missions that landed on the Moon. And it wasn't just a case of putting humans on the Moon. Those missions actually collected and brought back nearly 400 kilos of rocks from the surface of the Moon. And even towards the end, they even sent geologists on some of these missions so they could pick the most interesting rocks. And it's really from studying those samples in the laboratory that we've been able to piece together the history of the Moon and develop our understanding of the Moon having formed through a giant impact with the Earth early on in the solar system history. We also have about 300 grams of material that was collected by the Russian lunar spacecraft. So these were not putting people and not using humans to collect the samples, but these were spacecraft that actually scooped up soils off the Moon and brought those back. And so these have been really important samples for the last 50 years or so in understanding the history of the Moon and also the history of the Earth. And then in 2004, there was a NASA mission called Genesis. So this is in the bottom right corner here. And this actually collected high energy particles from the solar wind. So that the sun, our own sun, actually has a kind of wind of material that kind of blows through the solar system. And so the Genesis mission had these plates that you can kind of see these. And they kind of put these plates within the solar wind, and all those high energy particles were implanted below the surface, things like silicon wafers and diamond. And then this thing closed itself up and it came back to Earth in 2004. And we were able to use that to measure the composition of the sun. And in 2006, shortly after that, NASA's mission Stardust returned to Earth with samples from a comet. And so in this picture, you have this is the collecting mechanism that they had on the Stardust mission. This is a whole load of bricks made of a material called aerogel. This is a really low density material. And so this was exposed in the tail of the comet, and all the kind of dust particles that were coming off the comet became implanted below the surface of the aerogel. And then people have been studying the composition of these particles in order to understand materials that we find in comets and materials in the early solar system. And then in 2010, JAXA, the Japanese Space Agency, successfully returned samples from the surface of asteroid Itokawa with the Hayabusa mission. So Itokawa up here at the top, this unusual potato-shaped asteroid. And then, really excitingly, we have 2 further sample return missions at the moment. So Hayabusa 2, which is the follow-up to the Hayabusa mission, is currently on its way back from asteroid Ryugu, this kind of diamond-shaped asteroid. And so these samples are going to be back here on Earth at the end of 2020, which is really exciting. And then the NASA mission OSIRIS-REx, which is currently in orbit around asteroid Bennu, so very similar kind of shape to Ryugu. And it actually just yesterday did a test run for collecting samples off the surface, and it will actually scoop up some materials, or not quite scoop it, or kind of hoover up some materials, hopefully in the summer, in June, July time this year. And then those materials will be coming back to us in 2023. So this is all really exciting. anytime we get to do sample return, actually go out into the solar system and bring materials back to the Earth is a really exciting time for people like me who study extraterrestrial materials in the laboratory. So these missions are fantastic. They are incredibly expensive. They are incredibly challenging to do, so we don't get to do them very often. So those missions I just talked about are the only times that we've actually been able to bring materials back from other places within the solar system. Lots of spacecraft have gone to places in the solar system and observed them remotely. It's very rare that we actually bring materials back, partly because of cost, also technical limitations. These missions are also quite, they take a long time. They're not things that happen quickly. So for example, the Hayabusa 2 mission launched in, I can't remember now, 2014, Hayabusa 2 mission launched. So those samples aren't coming back again until the end of this year. So these are long duration, quite expensive, quite challenging missions. We're really lucky though that we kind of have a natural sample return mechanism, and this is in the form of meteorites. And so these are bits of rock from other places in the solar system that get knocked off the surfaces, travel through space. When we're really lucky, they'll actually come in through the Earth's atmosphere. They'll survive that process, land on the surface of the Earth, and when we pick them up, that's when we call them meteorites. So the chances of a meteorite landing on the Earth are exactly the same pretty much all over the surface. And so that means that most of those bits of rock that come in through the atmosphere actually end up in the Earth's oceans. And so we never get hold of those materials, and we never see those materials, unfortunately. Most meteorites then often will land in places that are uninhabited, so we don't really have people there. And so they'll just sit, nobody knows it's there, and we have to get lucky if we find those. But it is possible to find them, particularly if they land in desert environments, places that are very, very dry. And this includes both the hot deserts, so if you go to places in Australia or areas of America or in Africa and the Middle East. But this also includes places like Antarctica. People often don't think of Antarctica as a desert, but it's actually, despite all the water there, it's actually very, very dry. It's a frozen environment. And so meteorites can land in these places and actually sit on the surface of the Earth for thousands of years, relatively unaltered. You get some alteration from the terrestrial environment. The dry areas, it's much less significant than, say, if a meteorite fell in the back of your garden in the United Kingdom, where it's wet most of the time. So people actually, teams go out every year to search for meteorites in these desert environments. And one advantage you have is that when these things come in through the atmosphere, they tend to get kind of flash heated on the surface. So the outer sort of millimeters or so of these rocks gets kind of cooked. It's a little bit like making toast. And so they end up with this really black, shiny, what we call fusion crust on the outside. And so this makes them stand out on surfaces in deserts, particularly if you imagine going to Antarctica, where most of the surface is white. These kind of black, shiny rocks can actually sit there, and then makes them much easier for people to find these. And so teams go out and search deserts for meteorites fairly regularly. And these are what we call finds, these meteorites. And we have about, worldwide, there's probably over 60,000 meteorites these days. And most of those are meteorite finds, so things that were found by people and not seen coming in through the atmosphere. And you can actually go out and collect meteorites. Teams go, or NASA, for example, send a team to Antarctica every year. So they have lots of meteorites, and you can kind of write applications to get hold of those samples, so you can study those. And they often come in these big, huge boxes with good stickers on the side of them from NASA. If we're really lucky, we get meteorite falls, and these are when we actually see that meteorite coming in through the atmosphere. So this doesn't happen very often, but the advantage of this is that we can actually, if we have enough people witnessing that fall, and if we can capture it on camera even better, we can actually work out roughly whereabouts that meteorite came from within the solar system. We can't do that for finds. So for finds, we just have the rock, but we don't really know much about its origins in the solar system for most of them anyway. But if we see it coming in, we can actually try and backtrack out the orbit of that rock and try and work out whereabouts in our solar system it came from. But it also means we can work out whereabouts it would have landed on the Earth's surface. And this means that we're able to put together search teams really quickly, actually looking for these samples. And hopefully our aim is to try and collect them as quickly as possible. So this is really to minimize any alteration that they get from the terrestrial atmosphere. This is also one big advantage of sample return missions, is that we don't have quite such an issue because we're collecting the samples in space. We don't have problems with terrestrial atmosphere. So we really want to get falls. We don't have very many falls. Most meteorites are not falls, but as I said, I'll do a separate talk about how we can try and increase the number of meteorite falls that we have in our collections. So I'll do a quick kind of overview of the very broad classification of meteorites. The meteorite classification is very complicated, but I'll just do the kind of general classification that we use for meteorites. So there are three main types. We kind of split them up into iron meteorites, stony iron meteorites, and the stony meteorites. And then within that, the stones are split up into achondrites and chondrites, and I'll talk about those in a little bit more detail in a minute. And then within those chondrites, we also split those up into three main types. There are a few other types of chondrite, but there are three main groups, and that's the ordinary chondrites, the entite chondrites, and the carbonaceous chondrites. So if we start off talking about the iron meteorites, and these are exactly what the name suggests, these are lumps of iron metal. So unfortunately, I don't have any that I can kind of show you. Normally I would give people bits of iron meteorites to handle, but these are really, really dense. They're made up of iron, so about 90% iron and about 10% nickel in the minerals that are contained within these. So really heavy, really, really magnetic meteorites. So quite obvious when you get to hold them and you can put a magnet on them and things. And so they're really interesting. They have the amount of iron to nickel within these meteorites is actually quite unique to extraterrestrial materials. And so what it means is that we can actually identify things that have been made in ancient history using meteoritic iron. And so we know, for example, that the Egyptians were using iron meteorites to make jewelry and to make tools and things by measuring this iron-nickel ratio within those objects and comparing it to what we see in the meteorites. And often, because these things are made of iron, and because they're so heavy, that when these things come into the atmosphere, they tend to stay, they're really strong, they tend to stay solid materials, they don't often break up. And so when we see large impacts on the surface of the Earth, when you look at large impact basins on the surface of the Moon, for example, it was probably things like iron meteorites or iron-rich asteroids that created those huge impact craters, because these meteorites from these objects weren't breaking up in the atmosphere. Excuse me, they kind of stay solid and they smash into the surface of the planets. And so often when people talk about how dinosaurs might have been killed off by a large asteroid smashing into the surface of the Earth, so it was almost certainly an iron meteorite or an iron-rich asteroid that did that. And then we have the stony iron meteorites. And again, as the name suggests, these are a mixture, about 50% of that iron-nickel metal, but you also have a stony material. This stony material is actually a silicate mineral that we call olivine. So this is made up of magnesium, silicon, and oxygen, and you can see it in this image. It's these kind of greenish, browny green crystals. Olivine is really common on the Earth. So it's not completely unusual. People often think meteorites are made up of lots of strange elements and strange minerals that we don't find on the Earth, and that isn't true. Most of the solar system formed from the Earth formed from materials in the solar system, and most of the solar system will form similar kind of materials. And so, anyway, the stony iron meteorites have this kind of nice mixture. They're called pallasites. if you cut them really thin and put light through them, they're really spectacular. They're probably the most kind of visually spectacular meteorites that we have within our collections. Really popular on eBay and things for people making jewelry. Again, they're really heavy and magnetic to look at and to hold. And so we think that the iron meteorites and the stony iron meteorites are coming from large asteroids that formed within the early solar system. And on those large asteroids, you had the decay of radioactive elements, and the temperatures inside these bodies actually got hot enough to melt the rock. So these asteroids accrete all this kind of dusty material in the early solar system. They get bigger and bigger and bigger. And then as the temperature inside these bodies started to increase, that rock started to melt. And when you melt rock, it turns to a liquid and everything starts to separate out. So all the different components kind of start separating in a process that we call differentiation. So this is very similar to what happened on the Earth, where we kind of have an iron-rich core, and then we kind of have a rocky mantle, and then we have a crust. This is probably very similar to the structure that we had on asteroids like Vesta. So this is Vesta. This is the second largest asteroid that we find in the main asteroid belt that exists between Mars and Jupiter. And so this was visited by NASA's Dawn mission a few years ago. So this is why we have lots of fantastic high-resolution images of Vesta. And so we think inside this body in the early solar system, all the rocks became melted. All the heavy stuff sank towards the middle. So all the iron, being one of the densest elements, all sank towards the middle. And then the kind of lighter things, the magnesium, the silicon, and the oxygen kind of stayed above that in the mantle region. And then eventually these things, the source of radioactive decay kind of ran out. So these things started to cool down, and as they cool down, those rocks start to solidify. And so you end up with this iron core, and then this kind of rocky mantle, and then this kind of crust around the outside of that. And so we think the iron meteorites are representing the cores of these large asteroids in the early solar system. And the stony iron meteorites are probably representing the kind of rocky, mantle-y type materials that were around the cores. So you have this lighter olivine that didn't actually sink towards the dense center of these asteroids. There's also some models that suggest the stony irons may also have formed through impact melting. So when these large asteroids collided together, you also have a mechanism for generating really high temperatures and melting rock. And so impact maybe also played a really important role in creating the stony iron meteorites. We can actually date how old the iron meteorites are, and it turns out they probably formed within the first few million years of the solar system history. So we know the solar system's just over 4.5 billion years old, and these iron meteorites formed really early on, just a few million years after our solar system started forming. So this tells us that the kind of processes that went into making planets were happening really early in our solar system. It doesn't take very long to actually start making the kind of building blocks for the planets. Then we move on to the stony meteorites. And so as I said earlier, these are split into achondrites and chondrites. So starting with the achondrites, these don't contain chondrules. And I'll come back to what a chondrule is in a minute, but we don't find these in the achondrites. Most achondrites are kind of basaltic in composition. So they're very similar to the types of materials that you find coming out of volcanoes in places like Iceland or in Hawaii, for example. So these are basalts, volcanic rocks. And so this tells us, a bit like the irons and the stony irons, that they have to be coming from large objects where you had melting and volcanism taking place. So this has to be these big bodies that had enough heat within them to actually melt those rocks and allow these things to erupt out. So most of the achondrites that we find either come from Vesta. So we have a whole group of meteorites, or groups of meteorites called the Howardites and the eucrites and the diogenites that have been linked to the surface of Vesta. But we also have achondrites that come from Mars, so there are about 200 or so Martian meteorites, and we have about 200 or so lunar meteorites. So things that were made through the melting of rock on the Martian surface and on the moon. So the moon's really interesting because the moon's one place where we have about 200 or so lunar meteorites, but we don't know exactly whereabouts on the moon those meteorites come from. But we also have that kind of 400 kilos of material that were brought back by the Apollo astronauts, where we know exactly whereabouts on the surface of the moon those rocks were collected from. And then we have the chondrites. Most of our meteorites, about 60-odd thousand meteorites, nearly all of them are chondrites. These do contain chondrules, that's where the name comes from. And these are the samples that haven't been melted, they haven't come from bodies that underwent differentiation. So some of them got heated up a little bit, but those temperatures weren't high enough to actually melt those rocks. And so this is really important because melting kind of homogenizes and reprocesses all the materials that were originally in those asteroids. If you don't melt those rocks, that means those asteroids still contain all the original materials that were there within that protoplanetary disk. So all that stuff that was going around our early sun is locked up within these chondrite meteorites. And so they're a really important set of meteorites for understanding what the original materials, the original building blocks in our own solar system were. And as I said, there are several different groups of chondrites, but the main three are the ordinary, the entitite, and carbonaceous chondrites. So chondrites, this is a nice picture of a chondrite at the Natural History Museum in London. They're made up of three main components. The first is the chondrules, and the word chondrule comes from the Greek for grain. And these are kind of millimeter to centimeter sized spherical glassy objects that we find within the chondrite meteorites. So there's a couple of pictures. A picture of a chondrule that's been plucked out of a meteorite. This is a picture of a chondrule taken under an optical microscope. So this actually, a piece of rock has actually been, a piece of a meteorite has been polished down really, really thin. And then we use a microscope to actually look at the different minerals and the different textures that we see. So this is what we see down an optical microscope when we look at chondrules. So you can see they have both have these really, really round shapes. This has been cut and polished really thin. And so these tend to have really kind of glassy like textures. And so the idea is, or those textures kind of suggest to us that these formed from molten droplets in the early solar system. So there's lots of argument in the meteorite world about exactly how chondrules formed, but we think probably you had lots and lots of dust particles kind of accreting and starting to stick together in the protoplanetary disk. And then there was like a flash heating event that heated those things, those kind of collections of dust particles up to really high temperatures. It melted them, and then they cooled down really, really quickly to make these kind of little glassy objects. So it's kind of similar process to how you make glass by flash heating sand. And you end up with these kind of roundish objects because these things were spinning in the protoplanetary disk. And again, we can study these things and work out kind of what sort of temperatures they were getting to and how quickly they cooled down, and we can date how old they are. And again, these things formed really early on, so within the first few million years of the solar system. So these really were amongst the very first solid objects that formed within our own solar system. So before we had the planetary system that we see today, their protoplanetary disk was probably full of these things called chondrules, and they got swept up into making asteroids. The other component, or one of the other components we find within chondrites, are these things called calcium and aluminium rich inclusions. So this is an element map made using an electron microscope of a calcium and aluminium inclusion within a chondrite meteorite. And so in this map, the color red indicates iron within this sample. So this is kind of all the surrounding material. And then blue is calcium and green is aluminium. So you can see this object here is mainly made up of calcium and aluminium rich minerals. And these minerals are what we call refractory. So they condense out at really high temperatures. And so what we think was going on in the early solar system is the gas within that protoplanetary disk was really hot to begin with, and we had a really young sun, and that was generating lots and lots of energy and lots of heat. And then as the sun kind of settled down into its kind of normal lifetime, the gas within the protoplanetary disk starts to cool down. And then and as that cools down, different elements and different minerals will start to condense out of that gas. And calcium and aluminium as really refractory elements are the first things that started to condense out of the gas in the protoplanetary disk. And so you often find calcium and aluminium rich minerals are used in ceramics that you find in the back of ovens because they can survive being exposed to really high temperatures. And so again, we can date these, and we can study the different compositions of the minerals and the different types of minerals that you find within these what we call CAIs. And these are just a few million years older than the chondrules. So these are calcium and aluminium rich inclusions are the very first solid materials that formed within our own solar system. So we take these as kind of the age of CAIs as time zero for the solar system. So these condensed out from the gas as it started to cool down, and then chondrules started forming. And these things were going around in the protoplanetary disk, and they start getting swept up and accreted together to make asteroids. And so what we find then in the chondrites, that kind of holding the chondrules and the CAIs together, is the matrix. So this is kind of like the cement or the glue that kind of binds everything together. So this is what's helping this accretion process that's starting to make asteroids and larger objects. And the matrix tends to be very, very fine grained. So if you look at the kind of scale bars on these pictures, these scale bars are a bit dark, but these are about 1 micron in size. So the grains within the matrix are kind of micron to sub-micron in size. And so if you imagine a human hair is about the width, is about 50 to 100 microns or so in width. So these things are about 100 times or 50 times smaller than the width of a human hair. So really, really tiny, really challenging to actually study the composition and the different minerals that we find in the matrix. But really important because this matrix represents that dust that was in the protoplanetary disk. So if you think back all the way back to H.R. Tau, when I said you had these kind of bright regions where you have gas and dust, or some of that dust got swept up into these asteroids, and in some of these chondrites has remained basically unaltered since those bodies accreted together. So this is the dust from which the solar system formed. And we do know a little bit about it. So these are electron transparent foil. So these have actually been cut out of a meteorite and thinned down to about 100 nanometers or so. So thin enough that we can pass electrons through these things, and we can actually do things like diffraction experiments to learn what the mineralogy is and look at the chemistry. And we find the matrix is often made up of silicate minerals, so things like olivine that I mentioned earlier, but we also find bits of metal, iron sulfide, oxides like magnetite. Sometimes we see carbonates that have precipitated out from fluids. And then they also, in some of the least altered chondrite meteorites that we have, we also find pre-solar materials within the matrix. And so by pre-solar, I mean this is dust that formed before our solar system formed. So older than 4.5 billion years old. So this was dust that was condensed out around stars before our own sun had even formed. So this material was there in that protoplanetary disk, and in most of the meteorites that we study, it's been completely destroyed by all the processes that have happened to it over the last 4.5 billion years. But in the least altered meteorites, we still find those pre-solar materials, and we can use those, to understand what the materials were as our solar system was starting to form, and also use them to understand what happens in stars and how stars make the elements. So just to wrap up, I'll quickly talk about ordinary chondrites. So ordinary chondrites, over about 90% of all meteorites are ordinary chondrites, hence the name ordinary. As I said, they contain chondrules and some CAI matrix locked up within them. These come from small asteroids, probably from within the inner solar system. So we don't really see high abundances of volatile elements and things like water and carbon within these meteorites. And these asteroids were much smaller than those large bodies where we had melting and differentiation going on. But they still, so the rocks on these asteroids were never melted, so we don't have that recorded in the ordinary chondrites, but they were thermally metamorphosed to some degree, so they got up to a few hundred degrees C. So the ordinary chondrites do show what we call a petrologic range, going from not very heated to being much higher, having experienced much higher temperatures on the parent body, but not enough to actually melt these things and modify the components too much. They vary. Some ordinary chondrites have lots of metal, iron, nickel, metal in them. So that's the H types. Other ordinary chondrites have much lower amounts of nickel metal, so they're the L types. And so, yeah, these probably represent materials that were in the inner solar system during the early stages of solar system formation. Then we have the enstatite chondrites, and these are much rarer, and they have very unusual mineralogies. They tend to have lots of iron in metal and in lots of weird and interesting sulfide type minerals, and so this suggests they formed in a reducing environment rather than an oxygen rich environment. And they have been linked. They have some similarities to the surface of Mercury. So there was a mission called Messenger a couple of years ago, a NASA mission that studied the surface of Mercury and what that was made from. It doesn't look too dissimilar to what we see in the enstatite chondrites. And so this has led to the idea that the enstatite chondrites probably come from asteroids that formed really, really close to the sun. So they're samples of really the inner parts of the solar system. What's really interesting about the enstatite chondrites also is that they have oxygen isotopic compositions. So oxygen has 3 isotopes. That's oxygen 16, oxygen 17, oxygen 18, and the different amounts of each of those isotopes can vary between the meteorite groups and between different planetary bodies as well. So what we find in the enstatite chondrites is the oxygen isotopes actually are the best match that we have for the composition of oxygen on the Earth and on the Moon. And so we don't have very many enstatite chondrites really in the collection, but they seem like they were potentially a really important building block for making planets in the inner solar system. So the terrestrial planets like the Earth, but also Venus and Mars and things. So really interesting samples, the enstatite chondrites. And then we have the carbonaceous chondrites, and these are the things that I spend 99% of my time thinking about and analysing and studying. And so these are really important samples for trying to understand some of the most pristine materials that we have within the early solar system. So most of the ordinary chondrites haven't really had any significant alteration whatsoever. So they weren't heated up, for example, like the ordinary chondrites and the enstatite chondrites, and they weren't significantly altered by water like some of the other, like some carbonaceous chondrites. And so these are what we call the type 3 chondrites, so the unaltered materials. And so they really are preserving the building blocks. There's really really pristine, primitive materials in the early solar system that haven't been changed over the last 4.5 billion years. As I said, though, we do have some carbonaceous chondrites that contain minerals that interacted with water. So these are what we call phyllosilicate minerals. And so these are coming from asteroids that probably accreted ices. And in order for them to have accreted ices, they probably formed further away from the sun. So where temperatures were much colder, much cooler, so you could actually have ice within the protoplanetary disk. And so as that ice accreted into these asteroids, it started to melt. It reacted with all the chondrules and the CAIs and the matrix that was in there, and it transformed some of that material into these phyllosilicates. So what's really interesting, though, is that these kind of hydrated, these water-rich meteorites and these water-rich asteroids that formed in the outer parts of the solar system are potentially a way for bringing water to the inner solar system. So we know, for example, that the Earth has liquid water on it, that there's good evidence for there having been liquid water on the surface of Mars. It's very likely that the early Venus probably had water on it, very similar to the Earth. Mercury even has some kind of ices and some of the craters that are shaded and not exposed to the sun. And so we see evidence of water and other volatile species within the inner solar system. But we think temperatures in the early solar system were far too high for there ever to have been ices around. So you have to come up with a mechanism for delivering those volatiles. And one way you can do that is through things like the carbonaceous chondrites and through objects that formed in the outer part of the solar system. And these things were kicked in or migrated into the inner solar system. And the reason these things are called carbonaceous chondrites is that they contain a few weight percent. So some of the most carbon-rich things like the CI chondrites contain about 5 weight percent carbon actually locked up within these things. So it gives them a very dark, very black type appearance to them. And so these meteorites also contain organic materials. And so not only can they bring things like water to the early Earth, but potentially they can bring the kind of starting point for life. So not necessarily life, but all those kind of carbon and hydrogen and nitrogen components that you need in order for life to start starting to form are locked up within these carbonaceous chondrites. I think that's probably a good time for me to stop. So hopefully you found that interesting. And as I said, I'll try and do one more about, do a couple more, sorry, about meteors and fireballs and go into that in a little bit more detail. And another one about asteroids. So we use meteorites to learn about asteroids, and so introduce those as well. Hopefully, the kind of 3 things you've taken away from this are that meteorites are fragments of objects in space that land here on the Earth. So bits of asteroids, sometimes bits of the moon or bits of other planets such as Mars, and these get knocked off, travel through space, come in through the atmosphere. And if we're really lucky, we either see that and we go out and collect it, or we're able to actually go and find these things in desert environments. Meteorites are really important, as I said, for understanding what the materials were at the start of the solar system and how those materials have come together to actually create the planetary system that we see today. And some of these meteorites and some of these asteroids that they come from probably played a really important role in kickstarting life here on Earth. And so this is what I spend most of my time researching, is looking at these hydrated meteorites and trying to understand how they may have delivered volatiles and organic type materials to the early Earth. Thank you very much. I will stop there.